Symposium. And but Tom brought me down here. Before I knew it, I thought I was going to be sitting in some room with, asking Stephanie questions. Before I knew it, Tom was dragging me down some ravine in the middle of southern Ohio, just after it snowed, and all of a sudden I found myself standing in front of a big pile of mud. But it turns out this is a very important spot here. Tom illuminated my understanding of the significance. This is actually a section of ancient soil that had been thrust up by the advancing snout of the biggest, baddest, meanest ice sheet to grace the surface of the Earth during the last ice age. This is right at the snout of the Laurentide ice sheet. And this is a till unit that caps the entire sequence. And in this deposit are pieces of larch and spruce stumps that got pushed over by the advancing margin of this ice sheet. And these stumps date to about 24,000 years ago. That was done by radiocarbon dating. And even with using dendrochronology and combining that with radiocarbon, one can pinpoint the kill date of this thing within about 2 decades. So it's extraordinary. So I had this wonderful experience with Tom, and I thought for fun, I'd bring this piece of wood and let you inspect it. Go ahead, unwrap it and look at it. This is a tree that was killed by the biggest ice sheet on Earth, and this ice sheet's gone now. It's no longer. I think we'd all agree that the Laurentide ice sheet is gone.
No, there's still some at the Barnes Ice Cap.
Okay, well, with the exception, that's true. That's a good point, Roger. This diagram here is a famous depiction of the Laurentide ice sheet that was made by T.C. Chamberlain back in 1894. And T.C. Chamberlain was a very interesting fellow, and he came up with a hypothesis for what drove ice ages. But this was his depiction of the ice sheet. And it was the Erie sublobe that killed that tree there. And that would have been right here. And then in more modern, with modern technology and remote sensing, the development of digital elevation models, you can see the footprint of this. In this case, is the Michigan lobe. But that's the footprint of the Laurentide ice sheet. And as you can see, it left a spectacular moraine record on the surface of the Earth for us to decode and begin to understand the climate and cryospheric changes that occurred that accompanied this great warming that brought us into the present interglacial period. And I plotted University of Chicago here, not because that's where I was. Cincinnati's over here somewhere, but this is where T.C. Chamberlain was. He started the program there. So, but this ice sheet left a tremendous imprint, and we're sitting in it right now. But that's not the only glacier to have left an incredible footprint on the surface of the Earth. This is a scene that many of you probably recognize because we've shown it many times before. But this is on the other side of the planet at a place called Lake Bukaki in the Southern Alps of New Zealand. And as you can see, there's a tremendous complex of moraine ridges that were deposited by a glacier that oozed out of the spine of the Southern Alps and deposited these moraine ridges along its left lateral margin. This is a spectacular paleoclimate record imprinted on the landscape. It's trying to tell us about how the climate system works. And it's only been until recently that we actually have the tools that allow us to date these features. And I'll get into that in a moment. But one prominent morphological feature is this geomorphological break shown right here. And that marks the onset of the great recession of this glacier when it pulled away from its moraine belt and the ice retreated well back into the mountain valleys. And that is the footprint of the last glacial termination in the Southern Hemisphere on the opposite side of the planet from the Laurentide. This was a tremendous warming event. It's something that I began to study here at the University of Maine. So this is really building off my PhD work. So I thought it'd be appropriate to discuss this for an alumni lecture, something that the University of Maine has made great contributions to, and I'm just carrying along with some of the research. this is an important event because it was that event that established humans as we are today and led to our the growth of civilizations unlike anything the Earth has ever seen. And so I would say this is the most important climatic change in human history. And I would say, and one thing I'll try to show you is that I think that this was an incredibly rapid change too, perhaps much faster than anyone had previously thought. I think this was a global, abrupt climate event that propelled the Earth from the Ice Age to the present day climate condition. Now, the reason why we study glaciers is because they're exquisite thermometers. They're purely physical, geologic expressions of the climate system on the landscape. And they have, because they're completely physical, they have no strategy for survival. And so when it gets warm, glaciers melt. When it gets cold, glaciers grow. And glaciers exhibit a systematic link to something called the snow line. That's the level in the atmosphere where snow turns into rain. It's the freezing level of the atmosphere that's roughly consistent with the 0-degree isotherm in the atmosphere. Mountain glaciers on Earth that are in equilibrium with climate tend to exhibit a relatively simple geometrical relationship to the height of this snow line, shown in blue here, where 2/3 of glacier surface area will exist above the snow line, what's called the accumulation zone, and 1/3 will exist below the snow line. Any change in the height of that snow line will stimulate a response in the glacier system. And the nice thing is that glaciers tend to incorporate a lot of rock. This is the a large rock avalanche that poured over the ice field just a foot of Mount Cook. And for scale, see that tiny little red dot there? That's the hut that people stay in the night before they go summit Mount Cook, which is just off the photograph. So had this not been a warm day with a squishy snowpack, this rock avalanche could easily have just careened off this cliff and taken the hut out and all the people in it with it. This is how rocks get onto glaciers. And that was a few years ago. George and I went up there and viewed this by helicopter. And so these rocks are now being subducted into the accumulation zone. They're being covered in snow and being transported down the glacier system to where they then eventually will be deposited as moraines, such as these, that basically mark the footprint of the glacier at a specific time when it was in equilibrium with climate, could build a moraine. And we can use these moraines to reconstruct former glacial geometry and hence to reconstruct where the snow line in the atmosphere was, hence reconstruct climate. And now we're armed with a tool that allows us to systematically obtain accurate ages from these landforms. And this is called cosmogenic exposure dating, surface exposure dating. The way this works is that when a boulder such as this one falls off a glacier margin, it's exposed to the flux of cosmic rays coming from outer space, high energy particles that are coming in near the speed of light that collide with the atoms that make up quartz, silicon and oxygen. And they collide with such energies that they blast them apart and create a rare nuclide called beryllium-10. And that nuclide progressively builds up in the surface of the rock. So, and it builds up at a consistent rate. So it becomes a cosmic clock. And so what we do is we collect the sample, we bring it back to the UMaine Cosmogenic Isotope Laboratory, and then it goes through hell. It's crushed, it's pulverized, it's then leached in hydrofluoric acid and treated to several chromatography steps. And that eventually we end up with just a separate of the beryllium fraction from that quartz in that rock. It's weeks of preparation, and we send that to the Lawrence Livermore National Laboratory in Livermore, California, where they can measure the number of atoms to a tremendous level of precision, and we can determine an age from this surface. So we've been applying this all over the world to try to answer these questions of what drove the last glacial termination. But just to give you one example of what we can do with this method now, this is a glacier system at the spine of the Himalaya in Bhutan, just in the southern flank of the Bhutanese Himalaya. And this is a very fresh moraine that was deposited sometime, probably we assume in historical times, but we don't know because no one was there to observe it. We can now go to a moraine such as that and go to a boulder such as this, embedded in the ice contact slope of that moraine, take a sample with our Bhutanese colleagues using Roman technology, and get a piece of rock like that and take it back to the lab. And by developing geomorphologic maps, such as I've shown here, that delineate all of these moraine ridge features so we know exactly what we're dating, we can actually develop chronology. And this is one example. We now have a full chronology from this glacier system, but it's one example. That inner moraine that I showed you a few slides before, we can date to a precision of 1 sigma precision of plus or minus 10 years. So that moraine was formed in the year AD 1858 with a slop of about 10 years with no outliers. Now, not to say that, I mean, not every chronology is free of outliers, but it's a tool that can allow us to test many different climate problems from the perspective of Earth's mountain glaciers. Now, with regard to the problem of what caused the last glacial termination, we've targeted sites all around the planet. It's a global problem that demands a solution that is obtained from a suite of global results. And so a lot of our thinking began in the Southern Alps of New Zealand and Patagonia, and that's when I became involved with the project. And since it's spread to the Northern Hemisphere and all of these sites, as well as others, and these are just the places I work, and that doesn't include where other people in our group work. But we can now develop chronologies, not only for the timing of the onset of this great warming, but how quickly the glaciers retreated, and begin to address hypotheses for what caused the termination, and ultimately just to see how the climate system can behave, as a test of our understanding of the broad scale physics of the climate system. So as I said, a lot of our thinking came from the Southern Alps of New Zealand. And so I'll show you some of the work that we've done there. I'll briefly review some of this. But this is the geomorphological map showing all the glacier landforms in the Southern Alps of New Zealand that depict where these mountain glaciers sat during the last ice age in red. And we've applied this. And this is I want to show this slide because this is what I did as a PhD student here. And this was what at least got me thinking about this problem. Thanks to George and my committee for steering me in this direction. This is a chronology of a moraine set that now today impounds Lake Ohau in New Zealand. What we found is that this glacier achieved its maximum around 32,500 years ago, and underwent subsequent recession and re-advance. It deposited more moraines around 22,500 years ago, 18,200 years ago, and then the last prominent moraine ridge in this sequence that was deposited around 17,700 years ago. And I show these we call these camel plots, so basically probability distribution functions, but these just show how all the ages correspond on a given moraine ridge. So I'll show quite a few of these today. But this is an important moraine here because it was the last prominent morphological evidence for a robust ice margin in this valley. And one thing that I found surprising is that then we ventured half the way up the valley to a bedrock knoll here, sampled some boulders, and got some ages, and they're only a few hundred years younger. And that marks a 50% reduction in the length of that glacier. And so that would have been a fast recession, about 70 meters per year, plus or minus. But if you had been had a house up on the hill at that time, you would have noticed this recession in your lifetime. But it's one glacier in one valley, and so replication is key in this field, and chronology is key. So we went to several other valleys, and I won't show them all, but I'll just summarize another prominent valley that will also be featured in Courtney King's talk and Peter Strand's talk tomorrow. This is Lake Pukaki Valley. There's too many ages to plot here. We have over 250 surface exposure ages from this moraine belt, this set of moraine belts around this lake. But of relevance to our discussion today is the last major prominent position of that ice margin. That was held at around 18,100 years ago. This is based on 54 surface exposure ages. And Courtney's going to one-up this tomorrow, by the way. Those are just early days. Within 500 years, the ice had pulled back to within view of the modern glacier systems. Now we've done, so yeah, this is a figure that Peter Strand made to show this, but the glacier last held its position around 18,000 years ago, and by 17,500 years ago or so, these are a slightly different data set, the ice had pulled back up the valley somewhere close to its present day position. So this is an extraordinary deglaciation event. And we've addressed this in a number of different valleys, but one big question was, is this strictly a climate signal, or are there morphological influences, glaciological, glacier dynamics that can create an accelerated recession in response to a small climate formation of lakes, calving, issues like that? Those are relevant questions that we've been trying to address. So I just show one more chronology, and that's from a small hanging valley deep up within the Southern Alps that had, about 100 years ago, had a prominent glacier right here, and the snow line would have been roughly at the top of this moraine. And what we stumbled upon by accident was this moraine shown here in red. And now, the one important thing to know about moraines is that they only form in the ablation zone of a glacier, because in the accumulation zone, all the flow is convergent, materials being subducted, and then that's what reemerges at the ablation zone. So the snow line has to be above wherever a moraine is formed. And what we found was that this moraine, which is only 150 or 200 meters lower than the early 20th century, late 18th century or 19th century snow line, dates to 17,400 years ago. So this was a climatic warming that drove this ice recession to near Holocene values. So this is, we did not expect this. It's not fit our preconceived notion. And we've done a whole suite of modeling experiments with Shan, and this is one done by Nick Gollidge and a number of other people. We found that this warming was about the total glacial and interglacial warming was about 6.25 degrees. But the warming depicted by our record corresponds to about 4 degrees. And an additional degree happened during the Holocene, and another degree has happened over the past century. So the warming that we've documented from here to here is about 80% of the glacial and interglacial change. And in some of these valleys, it seems to have happened within less than a millennium. We've conducted multiple modeling experiments. So the question is was this something unique to New Zealand, or was this something registered more broadly in the Southern Hemisphere? So we went to southern tip of South America with this gentleman right here, who is also an alumnus of the Climate Change Institute, Charlie Porter. And Charlie guided us on his vessel, the Ocean Tramp, deep into the Chilean fjords, to dismal places like this. This is Pia Fjord in Cordillera Darwin. And a number of other people here have also been to this region with Charlie. This is Mount Darwin, named during the voyage of the Beagle, from what I understand. And there's a prominent glacier existing there today. And as you can see, there's all these spectacular ice molded bedrock features. And this would have all been covered in ice. And these maybe stood up as nunataks during the peak of the last ice age. And so we went around to boulders such as this. That's George's son there, Peter Wolcott. And we obtained some exposure ages. We were there with, again, Tom Lowell, Charlie, and then Brenda Hall, obtaining sediment cores to get radiocarbon dates for the onset of plant colonization, and thus minimum ages for when the ice sheet had to have gone away from the landscape. I will point out here that I'm taking the picture, okay? Charlie and Tom are yakking about something, and Brenda is carrying all of the equipment and pointing to where the work needs to get done. So this is not an anomaly. What we found was, and I'll try to summarize this here, is that some of the work that Jen Lennon did for her thesis is that the South Patagonian ice field last held its glacial maximum position around 18,300 years ago, and then by 17,400 years ago or so, the ice had receded way back right to near the modern ice margins. So the whole ice field had disintegrated by that time. And George and Patricio Moreno and a number of other folks have shown a very similar pattern from farther north up in the Chilean Lake District. It's an astonishing recession. And these just summarize the numbers that I just told you. We have this both with beryllium-10 and radiocarbon, two separate chronometers. What could possibly have driven such a rapid recession in the Southern Hemisphere? A number of ideas that we've played with. But I'm going to hold off on that and just point out this is, whatever caused it, it actually happened. It actually happened. So this yellow band here represents that interval of deglaciation, near complete deglaciation. Lake Bukaki, this is another valley in New Zealand, the Chilean Lake District, and Cordillera Darwin in the southern tip of Patagonia. So this is a broad swath of the Southern Hemisphere mid-latitudes, and it doesn't stand alone. I compare our, what we call the glacier inferred temperature record, which is developed from our chronologies and placed on a temperature scale using glaciological modeling, with the latest and greatest temperature reconstruction from the new West Antarctic Ice Sheet Divide Core. And as you can see, there's broad similarity between all of these moraine building events and cold periods registered in Antarctica. And also there's a very prominent warming registered right at the beginning of this interval that we call Heinrich Stadial 1. So this is, within a blink of an eye, the whole southern quarter of the planet seemed to have warmed up. And it was during this time called Heinrich Stadial 1. And as you can see, there are all these, what Heinrich stadials are these times in the North Atlantic region when the North Atlantic suddenly stratified, presumably in response to an influx of meltwater and icebergs coming from the great northern ice sheets that sat around the North Atlantic at that time. And it was a spectacular time in Earth's history. The Northern Hemisphere monsoon systems failed. The North Atlantic became covered in sea ice. The ITCZ shifted south, and the southern westerlies presumably shifted south too. And each one of these Heinrich stadials occurs in between a period of moraine building and during a relative warm period in Antarctica, with the biggest punch happening, this thing called Heinrich Stadial 1. So there seems to be a systematic link between the abrupt climate changes registered in the Northern Hemisphere and this phenomenal termination in the Southern Hemisphere. So after doing all that, it led us to the question, well, geez, I mean, never would have expected this from the chronology. We were expecting much slower recession, we're testing ideas about orbital forcing and what if the mountain glaciers in the Northern Hemisphere also have some secrets to tell us? And so that led us to think, well, okay, let's go somewhere where we might be able to address some of these questions. So we decided to go to the Cordillera of the Western United States. And one of the first places we visited was the Wind River Range in the interior of the western U.S. in the northern Rocky Mountains. And this is where the classic Pinedale terrain sequences exist. These were first noticed by Fremont himself, for which this lake is named Fremont Lake. And it was Fremont who led an expedition out here and surveyed this region that noticed these, what he called spectacular, these bouldery ridges around a jewel-like lake. And just because it's kind of interesting, Fremont then went and was a general under Lincoln during the Civil War and was a staunch abolitionist. He went down to Mississippi, I think, declared martial law and started freeing slaves without the permission from Lincoln. So Lincoln was not pleased with this and relieved him of command. But that just shows you what kind of character Fremont had. But he described a number of these areas in the western United States, and including this classic, what is now a classic set of moraines called the Pinedale Moraines, which is the type section for the glaciation of the Rocky Mountains. And Fremont is buried at the top of Clausland Mountain in New York, which is a few miles away from Lamont Doherty Earth Observatory. And one of the prominent directors of Lamont is also buried right next to Fremont too. So in a way, because a lot of this came out of our collaboration with Lamont, many of these ages, our getting here was both because of Fremont and Maurice Ewing at Lamont. But we did undertook a similar approach. And that's Catherine Laddig. This is part of her master's thesis for the Climate Change Institute. And she obtained a beautiful chronology, and we developed a geomorphological map and undertook the same exercise and found that the Ice Age the glaciers were building moraines around 20,000 years ago, 17,800 years ago, 16,800, and then about 15,850 years ago. So a little bit later than when the termination was registered in New Zealand. But shortly after this time, the ice receded well back up into the mountains. And this is a place I ventured to on horseback with Shan, shown for scale here at the bottom of the picture. That glacier had then rapidly cleared this valley. There's a lake glacial moraine, and the modern glacier is just around the corner. You can see some bits of the snowpack there. The ice had receded into that valley to a position very close to the little ice age position mapped here. So late, nearly historical position by around 14,800 years ago, roughly 15,000 years ago. So within a millennium, that ice cap was obliterated to its modern condition. That's an example of one of these old boulders perched right out in front of the little ice age moraine. And so we said, well, geez, maybe this is just a local phenomenon. So we went down to the Sierra Nevada to check it out in a place called Convict Lake. And in the interest of time, I won't go through all the gory details with you, but we did the same thing and basically found the same result. So this was a widespread, this chronology seems to hold fast across much of the western United States. And so we did Sean Burkle did the modeling for the Wind River Range and the Sierra Nevada, and we developed a glacier-derived temperature curve that shows shown right here. So the red dots are the average ages of all of our moraines, and this is and what we see is between about 16 and 15,000 years ago, near complete warming out of the Ice Age. And I've adjusted it here because we do know that in the Great Basin, that right by 16,000 years ago, the Great Lakes had risen to their maximums. There's about a doubling of precipitation at that time. So we've accounted for this in these simulations here. But as you can see, it doesn't really change the story. This is dominantly a temperature signal. And by the end of this period called Heinrich Stadio 1, the glaciers are back at their interglacial positions, more or less. So I compare here with in blue, the New Zealand curve. It's a little out of date now. We have a lot more numbers, but the overall structure hasn't changed. I'd say it's just gotten faster because these are all, I would say minimum limits for the snow line because they were deposited when the ice was out of equilibrium with climate. But the big story is that during this period when the North Atlantic was being flushed with meltwater and icebergs, the Ice Age came to an end both at 45 degrees south and 45 degrees north. This is an astonishing event. But maybe something's wrong with the Wind River Range. Maybe that's a local signal. Maybe the Laurentide, there's local atmospheric control. So this posed another problem. So where do we go to test whether this is a hemispheric signal? The same approach is what we applied in New Zealand. In the Southern Hemisphere, New Zealand, and then South America, and then Antarctica. Well, we thought the best place to go would be in the core of the Earth's largest continent, farthest removed from the ameliorating effects of the oceans, and on the opposite side of the hemisphere from the Great Laurentide ice sheet. So any local atmospheric effects, such as a big anticyclone that may have influenced the Wind River Range, would be less influential here, perhaps. So maybe I'm wrong about that. But this is a region in which the atmospheric temperature is dominated by the radiative heating of the land surface. So it's not only important because it's away from all these other places, but it's important because it's a place for testing the role of radiative forcing in driving glacial cycles, and it might teach us something about how it drives climate in general. So we went to the various changes of the Asian mountain ranges, and this is something that's relatively new, and that is a project we're actively working on. But one of the first places we went was the Tien Shan Mountains in western China. And this is a place called Urumqi Glacier number 1. it used to be one glacier and now it's two. So they're probably going to have to label it 1A and 1B. But it's one of the best monitored glacier systems in Asia. The Chinese have been monitoring mass balance on this for 50 years. A discharge, they have all meteorology has been monitored. So it's a very well understood glacier system, and it's been to be shown dominantly sensitive to temperature. This photograph is taken from the ice contact slope of the Little Ice Age moraine. And so this is a Google Earth image of that same glacier sequence, and you can see very prominent Little Ice Age moraines, young features. And then just outboard of that is a very subdued landscape, mantled with erratic boulders, vegetated. It looks much older than these deposits here. And so we developed a chronology. And the first thing we did was we wanted to make sure this truly was what we call the Little Ice Age. And so we obtained ages from two of these moraine ridges right here. And we determined that the outer moraine was deposited around the year 1656, plus or minus 6 years. That's 1 sigma error. And then 1848 with a 1 sigma error of 2 years. And those ages of moraine construction line up to within less than a decade of the historically known maxima of the Swiss glaciers. So it shows that A, this system is registering a broader climate pattern. And B, that that we can apply this method here and get it to work. But then what was perhaps most interesting, and I think this is perhaps the one most puzzling and exciting thing that we've stumbled upon in the past couple of years, is that here in the mid-latitudes in the Northern Hemisphere, in the center of Earth's largest continent, on the opposite side of the planet from New Zealand and all these other places in the Southern Hemisphere, the ice had retreated to within its Little Ice Age moraine by 16,500 years ago. And just for reference, a Chinese team had dated the last glacial maximum moraines well down the valley to about 18,000 years ago, plus or minus 500 years. So within 1,500 years, the entirety of the glacial interglacial change had occurred at this spot in the Northern Hemisphere. That's an example of one of these 16 to 17,000 year old boulders out in front of the Little Ice Age moraines. My father for scale. So what I've done here is I've plotted that age. So all the ages shown in red here are ages for when the ice had achieved an interglacial position. I should have mentioned that before. And all the ages in blue are for when the ice had maintained an ice age position. And so you can see the Tien Shan falls right on the just on the young side of this big interval of deglaciation in the Southern Hemisphere. So I can't help but wonder if that was a global event. This would have been, well, Shan's working on the modeling right now, but this would have been I'd say 6 to 8 degree warming, which is what it was in the Western United States. All within 1,000 years or so. Be like since the time of the Vikings for us. And so that's just one glacier, one valley, and we have a lot of work to do. So we just got funded for a proposal to work in 2 more places in Asia. This is what we're up to now. First is in the Altai of Mongolia, which contains spectacular glacial sequences that mirror those in New Zealand, that also have beautiful morphologic features that can allow us to track the recession, the rate of recession of these glaciers at the end of the last ice age. And then in the Himalayas, we want to do the same thing. This is along the northern flank of the Chinese Himalaya. And just to give you an example of this, last summer, as part of this project, we ventured out to the Mongolian Altai, and this is an example of one of the moraines deposited during the last ice age with beautiful polished granite boulders that can be dated with beryllium. This is the ice contact slope that was abandoned at the onset of this great recession. This is an example of a perched boulder that was draped onto the landscape as the ice was melting back all the way up into the valley. And one interesting thing about this valley is that the deglaciation presented a canvas on which the human history of Central Asia could be recorded. There are thousands and thousands of petroglyphs etched into the rock here. This is shown here, 2 back-to-back courses. These petroglyphs document when animals in the area went from being browsing animals to grazing animals. They document the domestication of the horse. They document the invention of stirrups, the use of chariots. It's an extraordinary place. And this all happened after the close of the Ice Age, and these beautiful striated and glacially polished landscapes were utilized for this purpose. And you can see them there today. So one aspect of our research is to look into this, too. We're working with some archaeologists from the Smithsonian, a fellow named Bill Fitzhugh, and some art historians trying to place this into the context of the climate history of the region. Some more examples there. But we've been working with a group of students or of researchers from the Mongolian University of Science and Technology. These are two of my students from 2 years ago, measuring the height of a boulder. And this past year, we had students from the Mongolian University of Science and Technology and students from University of Maine. And here, this is Caleb Ward from the University of Maine at Presque Isle. And these students are coming together and working together and trying to solve these problems together. And it's a learning experience for all of us in a beautiful landscape. And my Mongolian student created this for her senior thesis, a beautiful geomorphologic map of the LGM moraines. You can see it's all in Mongolian, except for the legend. She took mercy on us there. But this is something we're trying to do, is apply the same approach that we've applied elsewhere to these mountains of Mongolia. And now I won't try to steal all this thunder, but now Pete Strand is focusing on this area as part of his PhD, and he's just started developing a chronology. And what he's already shown is when the ice held its maximum position. But we're still waiting on the exciting results about when the ice had retreated up into the valley, and that's something that we're actively working on, and we anticipate eventually Peter will have this boulder dated, which is right in front of the little Ice Age moraines. So we hope to elucidate this interesting possibility that even Asia just warmed up dramatically out of the Ice Age. And so I don't want to hold you hostage for any longer, but I think what we've learned from this is one key factor, and that's, well, we've learned that the Ice Age came to an end in an incredibly abrupt fashion as monitored by highly sensitive mountain glaciers. In my mind, this shows that the Earth's system is capable of remarkable changes that would not have been predicted by looking at any of the other forcing factors, in my mind. It's an entire system reorganization. The system does not change smoothly, it changes abruptly, and it can happen globally, and that can involve the end of an ice age. And of course, we're still trying to figure out how insulation and how CO2 all factors into this, whether this is a nonlinear response to those forcing factors. But I think it's this big global experiment that played out 18,000 years ago is trying to tell us that the system can work this way. And now we're adding CO2 to the atmosphere, and it's warming up. And all of the models that are put in the IPCC generally tend to predict a linear response to the forcing. And I think this is something that Paul has reiterated many times. But what we see from the past is that the Earth doesn't operate in a linear fashion. And we don't know that there isn't some other warm mode hanging above our heads that the Earth could just snap into. And so that's one of the lessons I think we're starting to learn from the end of the last ice age. That's all I have for you today. So thank you very much, and I'll take any questions. Dan?
That was a great talk. Thanks. And it's not really a science-related question. It's more of a physics one. Those petroglyphs, how are they etched into the rock? How do they survive that long?
Well, maybe I should
in open to the weather and everything.
Yeah, see if I can. I mean, I think it's staggering how immaculate the preservation is here. It seems that they're pecked, and that someone here, I'm sure some of the archaeologists here could probably be more, give you a more definite definition. I think that the tools have changed through time. I think it's gone from bone to metal implements. But you can, I encourage anyone to try making an image like this. It's an incredible skill. What's interesting is that yeah, these surfaces that aren't pecked contain glacial polish, which is micron thick. So there's been no erosion on these surfaces. It's held fast. And these petroglyphs have held fast with it. And another interesting feature is that both in the glacial striations and in these petroglyphs are accumulations of what we call rock varnish. So this, I didn't get into this, but rock varnish is a metallic precipitate, basically, that forms when dew condenses and then evaporates off the rock. And the metals have probably been leached out of dust particles that then, predominantly manganese oxide, that form these tiny laminated deposits, almost like lake basins. And they actually contain stratigraphies. Now they're complicated, but we've been working with a fellow named Tien, who is an expert in reading these stratigraphies and taking tiny samples from these one little dimple, for example, in a piece of varnished petroglyph, and then a tiny sample from a striation to get a master chronology, and then see if we can't patch it in there almost like tree rings. So one thing that we're doing is actually trying to develop a chronology with the archaeologists for these generations of rock art. Now it sounds straightforward. It's not, and the varnish can be messed up. And so we're working through the trials and tribulations. But that seems to be what's happening. So if anything, there's actually these substances are grading onto these surfaces. The surfaces aren't eroding. It's probably part in part because it's really strong quartzite bedrock that just is hard to erode. Yeah. So, does anyone else have any comments on that, or archaeological?
I was just wondering if you did have a way, I assume you can at least get maximum ages by when the landscape at each place became ice-free. Has that helped at all in putting together the chronology of the images?
Well, that was our first task. Let's put a start date on all of this. And the estimates from the archaeological community had ranged from anything from 30,000 years ago to Holocene. Bill Fitzhugh wanted the deglaciation should be Holocene because he didn't think any of these petroglyphs could be Paleolithic, based on stylistic correlations to grave sites and things that have been dated that are associated with similar petroglyphs elsewhere in Mongolia. So at least I think
they still could be.
I think they still could be, right? Yeah, I think they still could be.
Directly.
Yeah, but now at least we and Peter Strand will show this tomorrow. I didn't show the age, but he has an age of this now, and so he is able to put a maximum age on the canvas.
Cool.
Yeah. Dan?
I'm going to ask you the statistics question again. I'm not going to talk about outliers tonight. I'm going to ask you, what are enough dates? You were showing some results based on 3 or even 6 dates, but then you showed concocted with 250. Don't you think that's a little overkill?
Well, Keck's a pretty nice place to work.
Yeah. But the precision of a date from a uniform population only increases as the square root of n.
Yeah.
So you start wasting resources.
Well, okay, so let me say that one thing that it was more of I think there was another hypothesis that we were testing there, and it wasn't, let's just date the same moraine ridge 500 times. It's we had to confirm that moraine ridge that we thought we could trace around the valley was indeed the same ice margin. And so it's been part of a bunch of different chronologies trying to tease out, because it's actually a complicated sequence. There's probably a little bit of uplift right at the head of Pukaki that's allowed for some of these older moraines to be preserved, because then they all converge and dive under the 20,000 year moraine down toward the end of the lake. And so part of it wasn't just to hit it with more dates than anyone could possibly argue with, although that certainly is our approach. But it was also to make sure that we weren't fooling ourselves as we were tracing that ice margin around, because that's what Shan needs to get a profile that he can then calibrate the UMIS and glacier simulation to. So you're probably right. You probably don't need too many more, but it wasn't the only reason.
There's a whole sequence of moraines ranging from 18,000 to 65,000 years ago.
Yeah.
All of them. There are probably about 40 of them. You have to date every one to get this thing straight, because to see if those moraines all fell, how they related to how they so it took 250 for them.
I thank you for this wonderful seminar. I have two questions. One is I grew up near Beijing, and I never get a chance to visit Mongolia or Xinjiang or Himalayas. And the question is, do you need a field assistant to go with you?
Who can speak Chinese?
I think that's really fascinating to say. But the second comments or the questions is really the role of the Pacific Ocean affecting the weather patterns and the climate in the Western China. I'll give you one example, is the dust activities from Gobi deserts and Talmahan, deserts. It's highly related to the winter temperature. That's how severe the dust, the storms you experience in Beijing and in Japan and is here in Acadia National Park. You can measure it. It has a strong the decadal signal. It's about a 25 to 30 years cycle. Because I know, I grew up in the area, and at certain periods, 20, 30 years, there was absolutely no dust. And then, for the last 20 years, the dust activity is much more severe. That is highly correlated to the temperature signals in the Pacific. It's the PDO, the Pacific Decadal Oscillation. So do not rule out the role of the ocean as a largest the thermal engine and affecting the weather. So that's the comment.
And let me clarify, I agree with you entirely. Let me clarify, I'm not trying to rule out the oceans, but I wanted to, we're working in the center of Earth's, most powerful ocean, or, right at the fringes of it, I guess, in Patagonia and New Zealand. So we want to go somewhere as far geographically removed to see what the differences would be, and to a place where the modern day temperature is I should say the seasonal cycle is basically in line with the insolation seasonal cycle. But I think you bring up a really interesting point. And so I mentioned this period of Heinrich Stadio 1. So that's now thought to be an incredibly winter-centric cooling in the North Atlantic. And you mentioned Asian dust. Those were periods of huge dust spikes in the Greenland ice core. And one explanation for that has been that the intensified seasonality led to just much stronger winds that could blow that off of Asia. And you even see the provenance shifted from between the Gobi and the Taklamakan Desert. That's measured from the sediments off in the Sea of Japan. And so there's definitely something really interesting going on. So I'll make one more interesting point, is that I almost made a figure that I didn't want to get bogged down in this because I thought you would probably throw a wrench into this, but I'll say it anyway, since you brought it up. If we were to take the average temperature anomaly for this year, pretty strong El Nino year, you would see anomalously warm temperatures pretty much everywhere on the planet except for blob right over in the western US. And also because the storm track was shifted, and that's also the precipitation's building up. So if I were to take that map and superimpose places where glaciers are receding around the planet during the last termination and where glaciers held fast, they would look identical. So one possibility is that the system got locked into some kind of El Nino-like state that was able to spread enough heat and water vapor around the planet to raise the snow lines really fast. Now that's not necessarily supported by all of it's hit or miss with the marine course in the tropical Pacific, but that could be one solution. And if so, I think that's a fairly powerful one. Roger.
I want to make a couple of points. One is that many of your uncertainties are plus or minus 500 years, and yet you're trying to narrow this down to maybe 1,000 years. The second point is that because of the response time of a glacier, You don't know whether it went up 4 degrees in 1,000 years or 4 degrees in 4 years, as has been suggested for the Greenland ice core.
That's absolutely right. And I wouldn't disagree with that. I'd say at best we can put a maximum estimate on that rate of warming. Because even if we could get the ages down to 2 years or whatever, the response time of the glaciers would still be struggling to catch up to something like that. So I agree entirely with the uncertainties, the analytical uncertainties reported by Livermore. Of course, what we're doing is we're combining them into these plots and everything. And what we do have to our advantage is geomorphology. So I guess maybe the most robust way of stating it is that within the uncertainties of our dating method, the ice age came to an end because we know it went from this position to that position, and that they can't be stratigraphically or they can't be inverted. So I think, and that's something we discussed with the Cordillera Darwin. It's not just with the beryllium; it's with the radiocarbon too. Bertha has a lot more information than I showed here, and we can't even resolve the differences between when the ice receded from the outer moraine and when the ice had retreated right to within nearby Marinelli Glacier. It's the probability curves are overlapping with one another. So we may have temporarily hit the limit of our precision, but I think that's telling us something really important. Yeah. George.
The fascinating analysis of the abrupt climate change at the end of the LGM is really wonderful. But there's another aspect of something you mentioned in your talk earlier on that has always puzzled me about this, and it strikes me as might be a clue to something important. And you mentioned going with Tom Lowell to look at that old till and finding that piece of wood you just passed around that dates to 24,000 or something. Well, we have at least 2 or 3 lakes in Maine where at the bottom of sediment cores, we have wood of that age. And that's not the age of the bottom of the lake, because the lakes are 10, 11, 12, 13,000 years old. These had to be wood washed out of the till, but it indicates the age when the trees were killed by the advancing ice. There's several of those in Maine. I think you might have mentioned one from the Southern Hemisphere. I can't remember if that was something like that. But what that makes me think, and I've thought about this for years, it seems to me what this is telling us is that the LGM itself, at least as expressed in these advanced moraines, itself was a very brief event. You know, that ice came, it didn't come and sit there very long. It came barely before it all disappeared, in a few thousand years before. And which makes me wonder whether it isn't that advance that's an anomaly itself, in the ice getting so far out of position that it had to melt fast when things reverted to normal in some. I mean, that's not quite the way to put it, but you see what I'm driving at here. If the advance is so briefly before all of that recession you were talking about, it seems to me there's an important clue there.
Maybe the Laurentide has a role in all of this, is what you're saying,
right?
Or Peltier and a number of other people have suggested that the ice sheet got so big it essentially depressed the lithosphere such that it could no longer withstand the snow line. But since you brought that up, I see if I can race back to one of those diagrams. 2 things that it made me think about. Now, the first one is that I think it's right. There's quite a few here, but I can't help but think about your record from Florida.
Lake Tulane,
And I think Lake Tulane would have. I think these bands are where the trees come in, right?
It's warm and wet at those times during the Heinrich times, when it was warm and wet in Florida.
Yeah. Well, and the mountain glaciers seem to be showing that too, responding to summer temperature. And then getting back to your point here, in the southern margin of the Laurentide, this is something I got out of my recent interaction with Tom, is that the southern margin of the Laurentide, although we think of it as this big beast that has long response times and everything, the southern lobes seem to have acted more like mountain glaciers. So of course, there's a much longer time scale involved in eliminating the ice sheet from the Earth. But these individual lobes seem to bear a chronology of advance that interfingers beautifully with the periods of moraine construction in both hemispheres.
That's what I was driving at. And
Yeah.
it seems to me there's something prompted that last advance.
Yeah.
That was a brief event.
Mhm.
You know, it's
Yeah.
kind of amazing that we
It wasn't a
can
very
find-
thick till. I mean, not
No,
thickness of a till really means anything, but
but you know, up in
Yeah.
Baxter Park area, the ice was pretty thick there.
yeah, it was. Yeah.
And that was the dates, I think it was Upper South Branch Pond, there's a piece of wood in that it's
Wow.
24,000 years old. It had to be over killed by that ice,
Mhm.
which is
It's-
pretty amazing.
It is. Yeah, I agree.
A couple of those lobes that you just pointed to are very likely surge lobes.
So Roger,
Yeah.
so how would one be able to diagnose that based on the geomorphologic record? I was because I saw a student give a talk on this, and I wanted your thoughts because I know you've worked on this a long time.
Yeah, well, I think there are a number of lines of evidence, among others, the nature of the till, the amount of disintegration features, like the slopes of the lobes as reconstructed are simply too low to support a normal advance. And I think that's true even to parts of North Dakota. Not only the Des Moines lobe, but whatever it is next to it.
James.
Yeah.
James lobe.
Well, that's a good point. So it could be, maybe we should be comparing them, or maybe any discrepancies might not be necessarily meaningful in a climatic sense. Peter?
There's one other chronometer that you have, a long wavelength chronometer, is the viscous response of the lower mantle particularly. So that puts some constraint on how long that load had to sit there prior to removal. It has a very long response time for that lower mantle. So the very, very quick loading and unloading would be a surprise to me from what we know about the response, particularly the lower mantle.
Yeah, but it would just be the edges that could be dynamic
Yeah,
though.
yeah.
The bulk of the mass of ice,
But
we know that from the isotopic record in the ocean too, that there was a lot of ice, but the edges could be pretty dynamic. I would
The
think.
edges are dynamic, I think, as well, but they're also, we know something about the size of those loads.
Yeah, well, I wasn't trying to imply that the ice sheet went away that rapidly, or,
No, I was actually wondering what the rest of that question was. Do you have evidence about the loading phase from any kind of, about the viscous response of the loading phase? Do you know of any place where that exists?
I personally don't.
Yeah.
But that doesn't mean it doesn't exist. Maybe, I don't know, someone else might have some ideas. I mean, maybe someone could do this is beyond my limits of understanding, but perhaps you could gain some insight, like doing the sea level, comparing the coral records and using a GIA model to tease out where the ice is growing when. But I think you need better sea level records before that could be done with a lot of certainty. Yeah. Mike?
Yeah, Aaron, you teased us at the beginning with driving factors or mechanisms for this, and then you said a perpetual El Nino cycle. Is that your best current thinking, or one of your top favorites driving mechanisms?
No, it's not my best. It's just, your mind tends to go that direction this year because you see the pattern that's unfolding. So that's the flavor of the year. No, I think there could be something to that. The pattern's right, but how that happens dynamically is another question. Another thought that we've been, now this is not mutually exclusive, but another idea that we've come up with that we've studied a little bit more is that when there's enough water to influx into the North Atlantic to shut it, basically stratify it. And with a freshwater lid, sea ice can then expand down to Portugal. And you get what's called the Heinrich belt, because the icebergs can be entrained in the sea ice and then melted at the edge. That's the severe Heinrich stadial wintertime phenomenon. That's the state. When that happens, and this is the work, some of the work that John Chang's done, is that the thermal gradient between the hemispheres relaxes. So the northern hemisphere starts to on average become more closer to the temperature of the southern hemisphere. So the thermal equator of the Earth shifts south, back towards the equator. I mean, today it's north of the equator because the northern hemisphere is warmer. And the hydrological cycle is basically pinned on the thermal equator. And so John Chang thinks that with a freshening and Heinrich stadial type condition in the North Atlantic, you get a southward shift of the ITCZ, which requires a compensation to allow for the conservation of angular momentum by the, so there's a compensation by the Hadley cells, which results in a southward shift to the southern westerlies. So it could be that a southward shift to the ITCZ would help invoke some situation in the tropical Pacific that could help heat the world in some degree, and also just shifting the westerlies south and stirring up the Southern Ocean. And Bob Anderson has also shown that there's a big pulse of upwelling at that time, and opal fluxes increased by an order of magnitude in the Southern Ocean. So Southern Ocean is definitely starting to de-stratify during Heinrich Stadial 1, and that would go a long way toward warming up the Southern Hemisphere. So what's puzzling me is what warmed up the Northern Hemisphere at that time. And it could be just a combination of insulation and CO2 forcing.
Why isn't it significantly CO2?
The reason I'm hesitant about CO2 is because the interglacial condition was achieved long before CO2 achieved its interglacial
But
condition.
it doesn't need to go, there are thresholds.
It would have to be a threshold. Yeah,
There
right.
are.
Right. It would have to
You
be.
said you were worried about a threshold in the future. Why couldn't there have been a threshold in the past?
Could have been. So I think if it were CO2, then it had to have been a nonlinear response
Well,
to
of
CO2.
course it's not linear.
Yeah.
The world is nonlinear.
Well, maybe that's trying to teach us something.
Well,
Yeah.
if you were asked in fourth grade class or seventh grade class, you told me that it warmed a degree in the last century. What's the primary reason for that happening? What would you tell that class? You'd say the greenhouse forcing is increased.
Yeah.
So why increasing greenhouse forcing wouldn't make the world in the southern hemisphere, in Patagonia, in North America, in Asia, increase in temperature?
Well, no, I agree with you. But I agree. And I think that is a valid solution. But it's been hard, even in getting our proposals back for review. You argue for an 80 ppm warming to drive the end of an ice age. You would have to invoke a really high sensitivity. And maybe that's what it's trying to tell us. Or maybe that's not what it is.
No, but you don't need that because at the termination, there's some conspiring going on between CO2, which will have a global impact, and the secondary impacts of increased greenhouse gases include meltback of sea ice, water vapor feedbacks, cloud feedbacks. And then on top of that, in the northern hemisphere, there's a conspiracy between the insulation, the Milankovitch forcing, which aided and abet the CO2 increase at the time of the termination, and the ocean circulation, which is perhaps told what to do by circulation changes in the atmosphere, could also do things to heat fluxes. So they all come together in a nonlinear dynamical system, but it could be driven by the CO2.
Could be, yeah. It could be. And if that's what was happening, then it's then it shows how powerful an influence CO2 has on our system.
Chamberlain would have agreed with me.
Yeah.
Chamberlain was 1899 published his theory of the ice ages, which was that CO2 drove ice ages.
And Tyndall said it in 1862.
Oh, did he? Yeah. It's a viable hypothesis.
Yeah.
Thanks, Aaron.
Just a reminder of everybody, light breakfast and coffee at 7:30, and we'll start at 8 o'clock sharp with tomorrow's talks. Poster people, please take your posters. I don't